Okay, let's look at Cauchy's integral formula. That's section 4.50. And we'll go through proof of this, an epsilon delta proof, classic analysis proof. And in the next section, we'll extend this to something a touch more general, a fair amount more general. The statement of Cauchy's integral formula, theorem 4.50.a, is let F be analytic everywhere inside and on simple closed contour C, where C is parameterized in a positive sense. If Z sub 0 is any point interior to C, then F of Z sub 0 equals 1 over 2 pi I, integral over C, F of Z dZ over Z minus Z sub 0. So one way we can use this is to evaluate this particular integral. The value of this integral would be cross multiplying 2 pi I times F of Z sub 0. Now, we had a hypothesis that F itself is analytic on and inside simple closed contour C. Now, the integrand isn't, because the integrand includes this Z minus Z sub 0 in the denominator, giving us division by 0 at Z sub 0. So the integrand isn't analytic on and inside contour C. If it was, Cauchy-Gersau would tell us the integral is 0. The integrand isn't analytic, but function F is, as described. So it has some constraints on the setting. Actually, we'll go through proof. Let's look at an illustration of it. Suppose C is a positively oriented circle, mod Z equals 2, and consider the integral over C of Z dZ over 9 minus Z squared, Z plus I. Okay, we want to make that look like Cauchy's integral formula up here. So we want to see a Z minus Z sub 0, where Z sub 0 is an interior point of the contour. Otherwise, the remainder of the integrand is an analytic function inside that contour. And we see we have some problems at plus or minus 3, but plus where we get division by 0, but plus or minus 3 aren't in the circle, mod Z equals 2. And we have a division by 0 at Z equals negative I, and negative I is in the circle mod Z equals 2. So for the analytic function, let's choose F of Z as Z divided by 9 minus Z squared. That is analytic on and inside, mod Z equals 2. That leaves us with the Z minus Z sub 0 part, where Z sub 0 is negative I. Negative I, got a minus up here and a plus down here, negative I to keep the books balanced. So we can rewrite the given integral in this form with Z sub 0 equals negative I, F of Z as stated. That means by Cauchy's integral formula, we can evaluate the integral. Cross multiply by the 2 pi I, the integral is rewritten in terms of F of Z and Z minus Z sub 0. Here's the integral. We'll cross multiply, get the 2 pi I times the function value at Z sub 0. The function we've chosen is as given, and Z sub 0 is negative I, so we'll plug negative I into this function F, giving us negative I in the numerator, 9 minus negative I squared in the denominator. The 2 pi I comes along from the cross multiplication, and when we simplify, we get pi fifths. So there's a way to use the Cauchy integral formula to evaluate an integral. Had to be an integral of a very particular sort, or else we couldn't apply the Cauchy's integral formula. But there's one application of it. When we look at the generalization, we'll see similar applications. Let's go through proof of it. I mean, there's nothing terribly immediately clear or intuitive about why this would be the case. So let's go through a proof. Okay. It isn't long, epsilon delta, good standard analysis proof. Okay, so let figure 66 describe the situation. So we've got contour C, oriented positively, so oriented counterclockwise. We're going to take C sub rho to be a little positively oriented circle, mod z minus z sub 0 equals rho. So a little circle of radius rho and center z sub 0, where rho is small enough that C sub rho is interior to the big outer contour C. So we know the interior of C is an open set. Z sub 0 is an interior point of that region. So there's a sufficiently small rho that'll allow us to choose a C sub rho of this sort. It's just elementary topology argument. Okay, so what we're going to do is make sure rho is sufficiently small that we can get some bounds on various things in an integral involving f. Okay, f of z equals, or the function f of z divided by z minus z sub 0 is analytic inside and on C, except at z sub 0. F of z was analytic on and inside C. So the only place we have a problem is at z sub 0. But by the principle of deformation, we know then if we integrate f of z over z minus z sub 0 about C or C sub rho, then we get the same values for integrals. Okay, let's maybe go back and take a look at that picture and see why that is. So we could deform C into C sub rho over the region about which the function is analytic. It's analytic inside C and outside C sub rho and on both of those contours. So principle of deformation says we could say that the integrals over C and C sub rho are the same. That's true if we made rho even smaller, which we're maybe about to do. We got to stay away from z sub 0 though in this conversation because that integrand is not analytic at z sub 0. So stay away from z sub 0 and we can claim that those two integrals have the same value. All right, what we're going to do is consider an integral over C of f of z dz over z minus z sub 0 minus f of z sub 0 times the integral over C sub rho dz z minus z sub 0. Okay, we got our reasons to be made a little clear shortly, but certainly that equals the integral over C sub rho, f of z minus f of z sub 0 over the common denominator, using the linearity of the integral and the fact that this integral over C is the same as the integral over C sub rho. Notice on the right-hand side, we have an integral over C sub rho. Okay, so we took the negative f of z inside, pull the integrals out one side and the dz's out the other. Linearity of the integral is what we've used. All right. Now, we know the integral over C sub rho of 1 over z minus z sub 0 is 2 pi I. That's one of the exercises. Notice the f of z is gone here. It's this little piece of the integrand, in fact. But the value of that integral is 2 pi I, exercise 42.10 part B, I suppose. So if we take this expression, we can replace this integral with the value 2 pi I, giving the integral we're interested in minus f of z sub 0 times 2 pi I equals this right-hand side, equation 4. So here's the plan. We're trying to show this integral equals this value. So we're actually trying to show this left-hand side equals 0. We're going to do so by showing the right-hand side must be 0, using epsilons and deltas. Okay, we were given that f is analytic. Analytic means differentiable over open regions. To us, differentiable implies continuous. So this function f is continuous on and throughout the interior of contour C. This function f is analytic at z sub 0. The integrand up here isn't, but the function f is. Okay, so let's use an epsilon delta definition of continuity. That means continuity at z sub 0 means for all epsilon greater than 0, there's a delta greater than 0, such that if mod z minus z sub 0 is less than delta, if z is sufficiently close to z sub 0, then f of z minus f of z sub 0 is less than this little positive quantity. Let's make that little positive quantity epsilon divided by 2 pi. It's a positive quantity. That's a definition of continuity. Why the 2 pi? You'll see shortly. It's got something to do with the circumference of a contour, a circular contour. Okay, but that can be done. That's simply the definition of continuity in terms of epsilons and deltas. Same thing you had in Calculus 1 for continuity in terms of epsilons and deltas, in fact. Now, in our little picture, the only restriction on rho in the picture above was that C sub rho was interior to C. So we're about to take rho and replace it with rho prime that might be a little bit smaller. So we're taking rho prime to be the minimum of the rho we had before and delta over 2. So in the picture on the previous slide, we've potentially taken a C sub rho prime that's smaller in radius. All these arguments hold in terms of inequalities and so forth. And we've got our reasons for doing this. What we're going to do next is take z to be on C sub rho prime. Then that tells us that z is really close to z sub 0. When z is really close to z sub 0, we get this bound on f of z minus f of z sub 0. Notice that's the numerator on the right-hand side of 4. Remember, we're trying to show this is 0. Okay, so let C sub rho, consider C sub rho prime. That's a contour with center z sub 0 and radius rho prime, this radius given here. That's definitely interior to C because it's no bigger than C sub rho, and C sub rho was interior to C in the picture. Everything we said about C sub rho, in particular equation 4, also holds for C sub rho prime. We could replace this integral over C sub rho with an integral over C sub rho prime in particular. If you like, it's the principle of deformation again. All right, so we're going to make an integral over C sub rho prime of this thing small. We're going to know how big the denominator is, and we're going to have a bound on the numerator, and then we're going to be in business. Okay. If z is on C sub rho prime, then mod z minus z sub 0 is rho prime. That's what C sub rho prime was, a little circle centered at z sub 0 with radius rho prime. So when z is on that circle, it's a distance rho prime from z sub 0. We've made z sub 0 so little, this is why we did that minimum thing, that we get rho prime less than delta. So rho prime is sufficiently small that we've got mod z minus z sub 0 less than delta. When mod z minus z sub 0 is less than delta, that definition of continuity told us the function values were close together. When the input values are close together within delta, the output values are close together within epsilon, or epsilon over 2 pi in this case. Okay, so when we look at this integrand over C sub rho prime, how big's that denominator? Rho prime, exactly. How big is the numerator? Well, we've got it bounded by this epsilon over 2 pi. So by theorem 4.43.a, modulus of the integral, we had bounds in terms of modulus of the function and in terms of the length of the contour. That's how we had dealt with that back in section 43. So we've got z minus z sub 0. That is modulus rho prime. The numerator is bounded by epsilon over 2 pi, as given here. Length of the curve. It's a circle of radius rho prime, so the circumference of that circle is 2 pi rho prime. Here's why we put the 2 pi in upstairs. This 2 pi cancels with that 2 pi. This rho prime cancels with that rho prime to give us epsilon. We've got this integral less than or equal to epsilon, where epsilon is an arbitrary real number. So we can write the integral that we had in terms of an integral over c, f of z dz, z minus z sub 0 minus 2 pi I, f of z sub 0. This was the left-hand side of the equation upstairs. We've got that less than epsilon, where epsilon is an arbitrary real number. So the only way this can happen, strictly speaking, we get a less than or equal to here from the inequality, from that inequality above, but good enough. Then the only way this can occur, since epsilon is arbitrary, is for the right-hand side to be 0. If the right-hand side is 0, the integral must equal this function value. This integral must equal 2 pi I f of z sub 0. And that's Cauchy's integral formula. So if you can handle epsilon delta definitions of continuity, along with a body of knowledge we know about bounds on integrals, then Cauchy's integral formula, it ain't so bad after all. And that takes care of section 4.50, Cauchy's integral formula. What we'll do in the next section is generalize it. Generalize it in terms of not function values, but values of the derivative of a function on the left-hand side. And that'll require some modifications, slight modifications on the right-hand side. And that will be totally useful, more than just for evaluating integrals. I'll see you there.